Okay, in this lecture we're looking at, I think, what should be perhaps assessment 2 material, equivalence relations and partitions. Okay, so we've started the ball up here. We've defined what a equivalence relation is. It's a relation, so a set of ordered pairs of a set. So here's a set of ordered pairs, both from a set. And it's an equivalence relation if it's reflexive, so that means if you draw the okay, so reflexive means that every element is related to itself, 0 0 1 1 2 2 3 3, or in terms of the digraph, every node has a loop. Symmetric if whenever say 0 is related to 2, you'll also have 2 is related to 0. In terms of the graph, every edge will be a double edge. And finally transitive, which is a bit harder to prove and harder to see in this picture, so we'll drive on from transitive. Okay, it can be shown that if R is an equivalence relation on X, that R partitions the set X into disjoint subsets. So this actually is what happened up here. So it partitions S into 0 and 2 and 1, 3. So it breaks it up into these blocks, and that's called a partition of the set. Disjoint means that their intersection is the empty set. So for example here, if I took A equal to the set 0, 2, and B to be the set 1, 3, it's actually missing a little bit. The partition means that if you take the union of all of them, you get the original set. So for example, A union B here, so that's 0, 2, 1, 3 is the original set, and the intersection of these two is the empty set. There's nothing in both sets. So that's what a partition is. Now that's a 2-block partition where there's just 2 parts, but there can be 3, 4, 5, infinitely many. Okay, so an example, let X be the set of students in this class, and let 2 people be related if they're born in the same year. So if P1 is born in the same year as P2. Now this is a reflexive relation because a person is born in the same year as themselves. Or is symmetric because if P1 is born in the same year as P2, say born in 2001, so then P2 is also, so if P1 is born in the same year as P2, say 2001, then P2 is also born in the same year as P1. It's completely symmetric. And it's also transitive because, say, if P1 is born in the same year as P2, say 1998, and P2 is born in the same year as P3, then P3 must also be born in 1998, and so P1 and P3 are born in the same year, so they're related. So this is an example of an equivalence relation. So if we represent this using a diagram, we should see how this forms a partition. So what exactly do I want to draw here? I'm not sure. So what I'm going to do is I'm going to draw, so we'll draw me anyway. I don't know, there might be mature students in the class, but anyway, here's me, and there might be a whole load of students. Now I'll only draw a few of them. Say that might be, I don't know, 2003, 2002, 2001. No, I'm going to draw, there should be way more. So these are just different students. I'll just number you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The labels, the names aren't important. So this is, I'm born in the same year as myself, 1985. So we said these are the 2003 people. So 1, 2, and 3 we're saying are all born in 2003. So 1 is born in the same year as itself, so is 2, so is 3. 1 and 2 are both 2003. 2 and 3 are both 2003. And 1 and 3 are both 2003. So then we got 2002. This one mightn't be so easy to draw. So I'm actually just not going to put on arrows because it'll just take too long. But loop, 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 related, 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 related. And all those edges are to be assumed double edges. Similar story here. Everyone is related to everyone else in that block. So this is, I think, 2001. And finally, the 2000. I missing anyone here? I don't think so. No. So this is the digraph of this relation. Now I'm obviously missing elements of it. So you can see the partition. So if I draw like a big set X is the students in the class. Now I've thrown myself in there as well. So maybe it's X union me, that we can partition it. So there's a 1985, 2003 people, 2002 people, 2001 people, the 2000 people, and then all the 90s and the 80s and the 70s and the 60s, whatever. So, and we can throw a label on each block. 1985, we said this was 2003, 2002, 2001. That's what it says right here, 2000. So this is what I mean by an equivalence relation forms a partition of the set into blocks. Okay, and everything within a block will be related to everything else in there. So like there's probably more than 4, 3. You know, there could be many more students. It's definitely, you can see. Now what's hard to see is the transitivity, but the symmetry is fine. I haven't drawn all the double edges, but they're all double edges. Every edge is a double edge. Everything's related to itself, and everything is transitive. Okay, so that's how an equivalence relation forms a partition. And notice that there's no person born in 2 different years. So that means that the intersection of any of these 2 blocks is empty. And if you union all these blocks, you get the full set of students together with myself. So this works the other way in that if you have a partition, that defines an equivalence relation. So for example, you can just take a set and partition it and say, oh, this is an equivalence relation. Everything in here is related to itself. Everything here is related to itself. Okay. Okay, I think, I'm not sure what I want to write. So we'd find a relation here. Oh yeah, sorry. So I think what we're saying here is that if we have a partition, we can form an equivalence relation. So let's take, and we'll keep S as or X as the set of students in this class, Comp 1C. So, and then we have the different class groups. I probably can't remember all these. So the groups are like web, software development, computer systems, IT, IT management. I think there's 2 software developments, so software development 8 as well. So okay, so we define a relation R on the set of students by student 1 is related to student 2 if student 1 and student 2 are in the same group. So the idea here is that if you have a set and you partition it, so all of you are in one of those groups, I don't think there's another one, and then you can just define an equivalence relation, say that, so these are the groups or the blocks, and say that 2 things are related if they're in the same block. Then you get an equivalence relation. Okay, so if R is a relation on R, then, we haven't said what this E of A is, and so E of A is, maybe we'll do that back here. So all the people in a block, so say take student 6 here, E6 is equal to the set of, say, students in the set X is the class, isn't it? Yeah. So it'll be all the students in the class that are related to 6. And this is called an equivalence class. And of course, you can take any representative in here. So the equivalence class, all the things that are related to 3, or, oh well, not the way I've done it, because I can't seem to count. 1, 2, 3, 4, 5, 6, 7. So all the things related to, and we can actually write this down here. So what are the people related to 6? Well, it's 4, 5, 6, 7. Well, those labels. Okay. And the equivalence class of 4 is the same thing. Who are all the people related to 4? 4, 5, 6, 7. What about 6? Well, 6 related to 4, 5, 6, 7, 7. 4, 5, 6, 7. And this is the sense that it's like equality, that they're kind of all the same. And that's the sense that it's equality. Okay. So these are the equivalence classes. And the equivalence classes are these blocks, basically, yeah. Right. And the thing that's saying here that if you have an equivalence relation, this should really say equivalence relation, that if you take all the ordered pairs, so you do the Cartesian product of the equivalence class of A, the equivalence class of A, then you get all of the relations. All of the ordered pairs. Okay, so that's a bit confusing. We'll just do an example. So what I'm going to do is I'm going to do this Cartesian product with itself, this Cartesian product with itself, this Cartesian product with itself, and then I'll put them all together as such, and that's how you can build a relation. So I'll just use colors to show this. So the first one. So do the Cartesian product of this block with itself. Remember, Cartesian product is you form all possible ordered pairs. The first thing is ADE and the second thing is ADE, rounding brackets. So AA, AD, AE, DA, DD, DE, and then finally EA, ED, EE. So that there is EA Cartesian product EA. So you make all the possible ordered pairs, the first thing in AD and the second thing in AD. And there should be 3 by 3, there should be 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9. Now what we'll do is we'll do EB Cartesian product EB. So this will be BB and BF. FB, FF. And the very last thing is this, all the ordered pairs. The first thing is C, the second thing is C, you only get one. Okay, so that is how you can build up an equivalence relation if you know the equivalence classes. I won't draw this. Okay, let's see some exam questions. Given the set 1, 3, 5, 9, 11, and the relation R and A given by this. Okay, so we're going to draw a diagraph of this. We're going to analyze it for reflexivity, symmetry, and transitivity. The best way to analyze a relation is using a digraph. So we're going to draw a digraph. Okay, so to draw a digraph, you take each element in the set on which the relation is defined and give it a node. So 1, 3, 5, 9, 11. Now there are other alternatives. You can do a coordinate graph, you can do an arrow diagram, but I strongly recommend the directed graph with the arrows. So what have we got? 1, 3, 5, 9, 11. And I recommend making nodes out of them like this. 1, 3, 5. Okay. And we join things with a directed edge if they are related. So what have we got? 1 is related to 1. 3 is related to 3. 3 is related to 1. 3 is related to 9. 9 is related to 3. 5 is related to 5. 11 is related to 5. 5 is related to 11, so that's a double edge. And finally, 11 is related to 11. I might just count 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. Okay, so that's the digraph. And this is what we'll use to study this thing. So, first off, is it reflexive. So you're going to have to internalize somehow what these mean. I think the exams may well be open book, but the time issue might mean you're going to be much better off knowing this stuff as if it was a closed book exam. So you're going to have to kind of understand, get some kind of an association in your head about what reflexive is, because I think it's very easy to confuse. Think of reflexive, it sounds like symmetric. I don't know. I think I probably usually think of a reflexive like reflective, looking in the mirror. It's the same thing related to yourself, something like that. Anyway, is it reflexive? Now, what is a wrong answer is to say, oh, it's reflexive, yes, because 1 is related to 1. That's not, you're not getting it. It has to be every single node is related to itself. So it's not reflexive because 9 is not related to 9. So we can answer 2 ways. Now, what you don't want to write is, oh, it's not reflexive. Not all nodes have loops. You need to specify. You only need one place where it fails. So we're going to go no. There's 2 answers. You either say 9 is not related to 9, so you can say 9 not related 9, or you can write 9 is not in the relation. That's fine. Or alternatively, which I actually recommend, use the digraph and say no, there's no loop at 9, which implies this. So that's that. Next question, is it symmetric? So is every edge a double edge? Now again, it is incorrect to say, oh, 3 is related to 9, 9 is related to 3, it's double edged, so it's symmetric. No, and there's no sense that you just say that 3 and 9 are symmetric. That's not really, it's the whole relation that is to be symmetric. And it doesn't matter that this is the double edge and this is the double edge. What matters is this is not a double edge. So the answer is no. And again, 2 answers. You can either say 3 is related to 1, but 1 is not related to 3. That's fine as an answer. Or you could write 3 is related to 1, 3, 1 is in the relation, but 1, 3 is not in. This dash means not. Okay. Alternatively, the edge from 3 to 1 is not a double edge. Edge 3 to 1 is not double. That implies either of these. Okay, and the last thing, transitive. So transitive means that that basically that there's shortcuts. Now this one, so if you can go somewhere in 2 hops, you can go there in 1. Now as they go, this one isn't too hard because it can be a little bit difficult to see this. So like an example, a weird example where this is transitive is, say you go from 11 is related to 5 and 5 is related to 5. Can you do that in one go? Yes. Or even 11 is related to 5 and 5 is related to 11. Can you do that in one go? Yes, you can go to 11 to 11. But that's going to be a harder one. An easier one is something like this. Is there a shortcut? So you can go from 9 to 3 and 3 to 1, but there's no shortcut. So it's not transitive. And if it's transitive again once, like say 11 to 5, 5 to 5, you can do it in 1. That doesn't make transitive. All possible times when you go in 2 jumps, you can do it in 1. So you just have to find one place where it fails. So 9 to 3, 3 to 1 fails because you can't do 9 to 1. So no. And again, the 2 answers. One is you can say, and we'll do it in, we'll give 3 answers here. They're all acceptable. So the first one is in this language. So we have 9 is related to 3. And 3 is related to 1. But, so 9 to 3, 3 to 1, double hop, 9 is not related to 1. So that means it's not transitive. So alternatively, you can write 9, 3 and 3, 1 are in the relation, but 9-1 is not in the relation. That's fine. And then the last one would be, you can go, so there's an edges even, 9-3, 3-1, but there's no shortcut, but no 9-1 edge. So that's how you do that. It is going to be a harder problem to say that something is transitive. You'll probably have to list everything. We may or may not see that. Okay. More examples. So this was a harder example, but we'll see how it goes. So let T be the set of all actors. Now, it's not very well defined, but presumably there's a definition somewhere of a film and someone that appears on screen in the film. You're going to get into issues with cartoons and stuff. Don't take it that seriously. We all can pretend we know what actors are. So for X and Y, so it's two actors, define two actors, X, Y in the relation, two actors to be related. Let's just put a little bit of English on this. So two actors, X and Y. Well, the first one, X relate to Y. Two actors are related. And the two actors, now the order, remember, matters. So the two actors are X and Y. If there is some movie that both X and Y appear in, which properties of equivalence relations does the relation R satisfy? Justify your answer. So this is a difficult question. Needed a bit of imagination, probably a bit of thought. And how would I think about it? So I'd probably go through each of them one by one. So first off, thinking about reflexive. So to be reflexive, an actor has to be related to itself. So is an actor related to itself, to him or herself or themselves? So if X is an actor, now it has to be an actor, and presumably to be an actor you have to be in some movie. This is where we get into problems, like it's a kind of a dangerous question really. But is there a movie that both X and X, so take, say for example Tom Hanks, is there a movie that Tom Hanks and Tom Hanks appears in? Yeah, I appreciate it. You could probably argue that. I think you have to say yes. Okay, so yes. So I'd say yes. Every actor appears in the same movie as themselves. So for example, whatever, Forrest Gump, Tom Hanks. Tom Hanks and Tom Hanks both appear in Forrest Gump. Yeah, that's fine. Okay. Symmetric. So if, say, let's take some actors there. Oh God, I can't even think of an actor. Probably think of some old thing. What did I say there? Tom Hanks. I'll take Tom Hanks. And again, sorry, Julia Roberts. So if Tom Hanks is in a movie with Julia Roberts, is Julia Roberts in a movie with Tom Hanks? Yeah, the same one. Yeah. So yes, it's symmetric. If X and Y are in same movie, so are Y and X. So it is symmetric. And then the last one is transitive. Now this one, it's probably hard to write a definite proof. I mean, ideally you want to actually think about an actual pair of actors, but like to show pointless, it's very hard to come up and be definitive. But you can just do an example. So I'm going to say it's actually not true. If I come up with an example, that'd be great. So I can think of maybe, I know, say Christopher Walken is in a film with Colin Farrell, and Colin Farrell is in a film with Brendan Gleeson. But I don't think, and I might be wrong, Christopher Walken is certainly not necessarily in the same film as Brendan Gleeson. So we might to argue here, probably no is the big thing, and to make an argument. So imagine these two actors in film 1 and these two actors in film 2. So this is film 1. So these two are in the same movie. And then this is film 2. These are in the same movie. Everyone is in the same movie as themselves. So that's what I mean by film 1, and that's what I mean by film 2. This is a difficult question. So this can happen, absolutely. So X can be in the same film as Y. Y can be in the same film as Z, but it doesn't follow that X and Z are in the same film. No. Possible actors X. It'd be great to come up with an example, but I don't think we can be that definitive. You can just imagine examples. So what we're saying, Christopher Walken, Colin Farrell, Brendan Gleeson, like that's in Bruges, 7 Psychopaths, but there's not necessarily a film that Christopher Walken and Brendan Gleeson are in. Possible X and Y in film 1, movie 1. Y and Z, which is a third actor, in movie. Sorry about the writing isn't great here. Movie 2. But X and Z never in the same movie. Doesn't really feel like maths because it's a little, maths usually can be so sure of yourself and stuff. Anyway, okay, that's our first video on equivalence relations.